Hi, hello, I'm Manlis, Francis, and I'm Paul and Michael. Uh, this is the electricity worksheet, the question 6 of paper 212223 of paper November 2019, the one that we didn't get to now last week or beginning of the week on Monday. So I thought of just going through it by looking at the question paper and the answers to it. There's some interesting and some nice questions. Right, let's start off by the first one is the fine electric potential, so potential difference. What is it? Please remember that we need to get full marks for definition. So what is potential difference? Potential difference is the work done per unit charge. Okay, so using this formula as your base, we can say the amount of work done per unit charge. Right. Okay, so now let's look at the next question. B, it says variation with potential difference of color and current is given for a semiconductor diode. A diode is shown. Now, we haven't had many diode questions previously, but look at this. We did do the theory on this. There is no current, and then the current starts increasing past a particular point. That particular point is 0.25 volt. This means if there's no current for that, it means it's got a very high resistance. So this is what we can say for the first bit. For 0 to 0.25, resistance is infinitely high since there's no current. Beyond that point, the current starts increasing and it has an exponential increase. We don't have to say anything about that. We can just say, because they're referring, what's the variation of resistance? Well, the resistance decreases. Right? The resistance decreases. You will get your mark for that. So 2 marks. The first mark is for stating that it's an infinite high resistance between those two values, and then stating that the resistance decreases beyond that point to 1 volt, because that's what the graph tells us. So just literally what is given in the graph. I'm going to keep the graph close by because we're going to use it in the next question as well. And says the diode in B is part of a circuit as shown, right? Remember, what's the function of a diode? It allows current to flow only in one direction. So the way that it is applied, current can move through it in that direction. The cell of electromotive force, EMF, 2 volt, negligible internal resistance, we're always happy to see that, is connected in a series with a diode and 2 resistors X and Y. The resistance of Y is 60 ohm. Current in the cell is 15 milliamperes. Okay, so that's all shown in our diagram as well. Use figure 6.1, your graph, to determine the resistance of the diode. Okay, so what do we need to get? If we want resistance, resistance is potential difference divided by current. So for a particular current, my diode would have a particular potential difference. So do this, please do this. If we know the current is that, use a ruler, dotted line, there we go, it crosses, come down, and it's 0.75 volt. Show this on your graph in your question paper. Then you can quickly refer back to it as well, and it helps you not to make a mistake. So, and this was actually not bad. 2 values of formula, and then for your answer, 50 ohm. Remember, it's milliohm, so times 10 to the negative 3. Next question. Calculate the resistance of X. Okay, we want the resistance of X. We've got the resistance of Y. We know of our diode, which was 50 ohm. We also know that the potential difference over this was the 0.75 volt. So if we had a voltmeter around there, that's what that voltmeter would read. Can we get the potential difference over Y? Yes, we can, because we've got the resistance, we've got the current, and if we have that, we can get the potential difference over Y. Why do I want that? Well, if I know what the potential difference over the two of these resistors are, I can get the potential difference over X. Having my potential difference over X, remember, my V in here is equal to the sum, or my PD over my battery is equal to my PD, the sum of the PDs over my resistor. So that's how I can get X. So showing you X, and I get X as 0.35 volts. Once I have the potential difference, my current in the series circuit stays constant as 15 milliamperes. I can calculate my resistance, 23 ohm. Right? Looking at my ratio for power dissipated, so power is VI. We've got my potential difference and the current for resistor Y. It is a 0.9 and the current of that. Remember, we said that we calculated that already. So 0.9, we know my current stays the same in a series circuit. So we've got that. We also know that's the current in my battery, and my EMF is that potential difference over my battery. There's no internal resistance. So that's the values that I use and get to my ratio. And remember, a ratio is always in decimal numbers, in a decimal form. Right? All of my values given, my data, is to two significant figures. So remember, my answer should also be to two significant figures. Remember that, please. So that was my first question, 11 marks. And this is what you can expect in the exam. Out of the 60, your paper 2, anything between 9 and 12 marks is going to be electricity. Okay, let's start with Kirchhoff's first law. Again, a law. Kirchhoff's first law, the sum of currents into a node or a junction is equal to the sum of the currents leaving or going out of that node or junction. That's Kirchhoff's first law. The variation of potential difference in current for resistor X. So now, again, potential difference in current for this diode is given. You can see the diode, again, infinitely high resistance and beyond a specific point, a threshold frequency of, let's call it a threshold point. There's enough energy and there's breakthrough and resistance starts decreasing exponentially. So my current picks up exponentially. My resistor X is directly proportional, so we know it's an ohmic conductor. That's what we can get from that. That says, determine the resistance for the diode for a potential difference of 0.6 volt. Okay, so if we know the potential difference is 0.6, we can go and read down the current. And again, the current is in milliampere. Using my formula, R equals V over I, that's 1 mark. Getting the read down value, and remember it's milli, so times 10 to the negative 3, and we get our resistance of 80 ohm. And then again, just a question relating to the graph. Describe quantitatively, the variation of the resistance of the diode as V increases from 0.6 to 0.75. What happens in this? Well, because my current increases, my resistance decreases. Remember this from my formula RV over I. What happens to my resistance? What happens? My current is increasing, so my resistance is decreasing. So R is inversely proportional to I. Right? Let's look at number C, question number C here. So a nice few questions, and again, they bring it all back to the graph. You always need your graph close by. So now, let's read the question. The diode and the resistor X are connected into the circuit. So there's my diode, there's X, and there's Y. And we're applying Kirchhoff's law quickly, just before anything is asked in the questions. Here we go. So if my current in the mainstream is 9.3 milliampere, this current is 7.5, and this, it splits up and it is 1.8 milliampere in that. Remember, into the junction equal to the sum out of the junction. The cell has an EMF and a negligible internal resistance. The resistor Y is connected parallel to resistor X and a diode. The current in the cell is 9.3 and the current diode 7.5. Use figure 6.1 to determine E. Right? How on earth can we do that? Well, look at what we have on our graph. We have resistor X and my diode. And just remember the following. In a parallel circuit, just get a different pen over here. My potential difference in there is equal to my potential difference across both. That's a very important fact. They're going to ask that in some principle right at the end again to make sure you understand that. And why is this like this? Well, it's Kirchhoff's second law, right? Sum of the EMFs is equal to the sum of the PDs. So whatever the energy is in there should be dissipated in this closed loop. If not, we're creating energy going through that. And if you can do that, you're a multi-billionaire. Stop coming to my class if you can do that. But for all our normal people out there, we can't do it. So the energy from my battery is dissipated in those two resistors. And so just again, sum of the EMF equals sum of PDs in a closed loop. Kirchhoff's second law must apply, and that's the reason for this. Why did I say that? Well, that means if I know from my graph, this is my current, I can make my read-offs, right? What is my potential difference over resistor X at 0.75 milliampere, or 7.5 milliampere? It is 0.3 volt. What is my potential difference in my diode at 7.5 milliamperes? It's 0.6 volt. So the sum of the two must equal my EMF. So actually that formula should be stated in there to make it a nice, and it should be a 2-mark question. You know, but there we go. So it's 0.3 plus 6, we get 9 volt in there. It probably, if they said use the graph and Kirchhoff's second law, then it would have been 2 marks. Well, you had to use it in any case. Determine the resistance of resistor Y. Well, you know what? Same principle. It's still the same. It's a different loop though, but it means that the potential difference over Y is the same as my EMF. That is also going to be 0.9 volt. It's the same. Same principle applies. It's just a different loop that we are using. So coming back to my formula, R equals V over I. We have my potential difference, and then the current going through there, the one that I actually did with Kirchhoff's first law. So it's 1.8 milliampere. You can show it like this. That's the 9.3 minus 7.5 times 10 to a negative 3. That is 1.8 times 10 to a negative 3. And we get to 500 ohm. Again, 2 marks for that question. Calculate the power dissipated in the diode. Okay, well, we've done power now a few times. Power is potential difference times current. We have the current by diode. I have the potential difference. I can calculate my power. That's fine. Shoot, guys. IV. What a question. I was dumbstruck by it at first, but let's read through it. The cell is now replaced by a new cell, EMF 0.5, and negligible internal resistance. Use figure 6.1, use the graph to determine the new current in the diode. If we apply our starting principle, the one that we did right in the beginning, where we said EMF, if sum of the EMF is equal to the potential difference. That means my EMF now in the second situation is 0.5 volt. That means the sum of these two, sum of the potential difference over my diode plus the sum of my potential difference in over X must equal 0.5. Let's use our graph. You're going to kick yourself. At 0, the sum of the two potential difference is 0.2, so total EMF of 0.2. That's not what it is. At my next point, so I'm doing this by inspection. At 0.1 volt, my current is 2.5. What is my potential difference over my diode? Well, it's 0.4. What is 0.1 plus 0.4 give me? Yeah, you're right. It's 0.5. That means the current is 2.5 milliamperes. So it's only by inspection that you could have done this calculation. And knowing that the potential difference over my diode plus the potential difference over X would give me my total EMF. So by inspection only we could have done this. I don't know, if you used a different method, so 2.5 milliampere is my answer. So there is a 0.1 volt cross X and a 0.4 volt cross I diode. And that gets to the 2.5 milliampere, or at that's where it is. And that is equal to my EMF, which is the 0.5 volt. Right. So I can honestly say I left this question and it took me a while to get to that 1 mark. What would I do in an exam? I would leave it to last. If there's time, I will come back to it. And it's one of those 1 mark questions that separates the A plus from the A candidates. And in this case, I wasn't an A plus candidate. I wouldn't have gotten it under that time pressure. I would have left it. One needs to think about it a bit. But hopefully now that you saw it, you will get it. All right, let's move on to my last question. And I did a bit of fetching over here already, so apologies. We'll see what it is as we go through it. So A battery with an EMF of 12 volt and a negligible internal resistance is connected to a network of 2 lamps. So there's my 2 lamps. It's, do they say identical lamps? And 2 resistance are shown. Yeah, they do. They say the 2 lamps have an equal resistance. They could have said identical. Right, the 2 resistors have a resistance of R and 28 ohm. The lamps are connected over junction X and the resistor over connected at junction Y. Okay, the current in the battery is 0.5 ampere and the current in the lamps 0.2 ampere. So immediately this is what I can say and can do. Because my main current is 0.5 and this is a junction, my current splits. So in the one branch is 0.2 and the other branch it must be 0.3 ampere. Same principle. This is nothing else than a branch. Listen, they're drawing it weird. There's nothing else that's drawing it. I'm just going to take this away. So that drawing could have looked like this. There's my branch. There's my one. And then over here is my bulb and another bulb. And coming back. And then they could have had this. That was R and my 28 ohm in there. That's a different way of drawing it. And that's mostly what you use, that being point X, that being point Y. The same principle applies. There's no internal resistance, so if this is 12 volt, my EMF, the total over those two would be 12 volt each. Right? The same over this. This is 12 volt because we're applying Kirchhoff's laws. If we're working in this loop, right, EMF equal to the sum of the potential differences. If we're using the big loop, again, same principle using Kirchhoff's second law in there. So because we also know these are identical light bulbs, that is 6 volt, that is 6 volt. They gave us the current as 0.5 ampere in there, and through my bulbs is 0.2 ampere. That's why I said in this one, 0.3 ampere. Done and dusted. We know that bit of information. Now, let's go back to the questions. They ask the resistance of each lamp. Well, we just said, and I did over here as well, because we know it's identical, 12 volt over both of them, identical, so it's 6 volt per lamp. We know the current through it. Oh, what a nice equation. And there we have it. Calculate the resistance of R, right? Okay, so show it. Yes, I know we indicated it on the sketch, but show you have your current. I want to calculate the total resistance of this branch. Because if I do that, look at it, total V over I, the total on that is 12 volt, the current is 3. Then you know my 2 resistors should add up to 40 ohm. So resistor R plus 28 should add up to 40 ohm. If I subtract my 28 from my 40, what do I end up with? I end up with 12. You could have done it in one step by substituting that part in there and gotten it that way. It's okay. No worries about it. Question B. Now they ask, if we were to put a voltmeter across X and Y, what would that voltmeter's reading be? It says determine the potential difference XY between the points X, and Y. So what does a voltmeter do? It determines the difference in potential energy. So we have a certain amount of potential energy. We have that 12 volts, right? So 12 volt and 12 volt in that branch and 12 volt in that branch. How much energy has been transferred in that first bit? Remember, because this is how my current goes. So let's think about that. What's the energy transfer in that bit? Well, 6 volt, isn't it? What's the amount of energy transferred to R? Well, I don't know, but I can calculate it because my potential difference, V, is equal to R times I. So the 0.3 times the 12 ohms. So we can do that. I've shown both. I can calculate the potential difference across a lamp. That's my 6 volt. The potential difference across that is 3.6. So what's the difference in the potential was transferred there to there? That gives me my potential difference. It gives me my reading. So it's the 6 volt minus the 3.6. So my reading is going to be 2.4. I think we did 1 or 2 questions like those previously in worksheets. So heads up, a nice question. Right, let's deal with the last bit, going into our last section. Again, calculate the ratio of total power dissipated by the lamps and total power dissipated by the battery. Well, total power, that's in one branch, so it's 12 volts. The current in there is 0.2. So I'm using my formula again, P equals VI. Total power produced by the battery, well, we know the EMF and the current in my main circuit, and we get to a ratio, remember, always in decimal numbers. And if it was perhaps more correct to stay to 2 significant figures, there we go. Always to 2 significant figures. I would have given 3 marks for the last question. I would have given myself a bonus mark. My goodness. Okay, so the resistor of resistance R is now replaced with another resistor, a lower resistance. State and explain the effect, if any, of this change in the ratio in C. So we must bring this back to my ratio. What was my ratio? It's power dissipated by the lamps and power produced by the battery, right? And we're going to work with this relationship, the VI. Is there anything that changes with my lamps? No. The EMF stays the same, so the power stays the same, right? There's nothing changed with the EMF, there's nothing changed with the power. But if we look at R and we decrease its resistance, we are decreasing the total resistance in my circuit. If my total resistance decreases, it's inversely proportional to my current, therefore my current would increase. Again, EMF is constant, but because we're using power VI, my V stays constant, I is going to increase, my main current is going to increase. That increases the power dissipated or produced by my battery. So in my ratio, if my power of the lamp stays the same, but the power of my battery increases, my ratio is going to decrease. So you're going to get a mark for saying the ratio decreases, and you're going to get a mark actually for saying this, well, that's why I say 3 marks. I would have said the power, the lamp staying constant, and that being changed in there. Right? I hope that made sense to you guys, and I hope this is successful like this. Good luck for tomorrow's test. Obviously, we'll go through that as well, and it's a learning experience. And it's just your exam that's going to count this trimester. Good luck. Ask if there's any questions. Bye-bye for now.